So good morning everyone. Today we will start with infinite impulse response filters. Okay. So in our last class we have looked into the FIR filter. Last class means the last few of the classes we have discussed about the finite impulse response filters, right? And over there we have seen that the filter coefficients they are what do you call they are limited in time limited, and you have specific numbers of those filters over there, right? Unlike the FIR filter, when we talk about the IR filters, these IR filters they will be having these filter coefficients which are undefined, which may extend up to the infinity. What I mean to say for example, if at time t tending to infinity, we will be having some hn values. However, these hn values they will be tending to 0. Okay. So if it is a stable filter, so this is the one of the important difference between the FIR filter and the IR filter. FIR filter they have limited number of HNs, whereas the IR filters they have infinite series of HN values. Okay. Now in our few classes we have discussed that the equation of a generic FIR filter would be something like this, and the equation for a generic IR filter it would be something like this. Now if we want to find out the difference equation, or we want to find out the pole zero plot, we have discussed that we need to multiply both the numerator and the denominator with z to the power n, where n being the highest degree of the z. Okay. So z to the power minus 2 or z to the power minus n, whatever, whether it is in the numerator or the denominator. So if you see, for the IR filter, this equation is the generic equation for a two-pole filter. Okay. Now if you simplify this and find out the difference equation, it would be something like this. Okay. And again, if I want to realize this, the realization would be something like this. Okay. Now if you see this equation carefully, so what happens, the current output of the system, it is dependent on the past outputs of the system. Okay. It is not only dependent on the present and the past inputs, but also on the past outputs also. And what does this mean? This means that the IR filters they are feedback filters. Okay. Say for example, in your analog class, you must have designed inverting amplifier, non-inverting amplifier, right, and so on. So those are feedback filters or amplifiers. So these kind of systems they can be designed using the IR filter methodology. Okay. Now coming to an example, initially we are taking a single pole example, and it is a generic example. If you see a single pole IR filter, it may be given by Az equals to 1 by 1 minus Az, where A can be any real number or decimal number, whatever. Okay. So if you want to find out the pole zero location, so if you see over here that we will be having a 0 at z equals to 0 and a pole at z equals to a. Okay. Now let us take a couple of cases where a is equal to 0.5, a is equal to 1, and a is equal to 1.5. Okay. Now what happens from here? If I draw the what do you call this realize the filter, okay, or draw the signal flow graph, so it would be something like this, and our pole zero plot would be something like this when a is equal to 0.5. Now I have told you that how to calculate the find out the HN values from the realization of the filter. realized filter. So you give the delta n value at the input, and you need to calculate the Hn values at the output. Now if you look over here, when we are giving delta n value as the input, our yn values or the Hn values, they would be 1, 0.5, 0.25 and 0.125 and so on. It will be going on. So at t tending to infinity, you will be finding that it is having some n values, Hn values, but that would be tending to 0. Okay. When a is equal to 1, the same architecture, it would be giving an output of 1, which is continuing up to 1. So if you see the output in the second case, it is neither growing nor decreasing. What it is? Hn. The Hn values, they are neither increasing nor they are decreasing. That means this kind of system where we place poles onto the unit circle, they are marginally stable systems. Okay, because they are neither going out of bound, the output is going out of bound, neither it is subsiding towards the 0. Okay. On the contrary, when we place this pole outside, that is when the value of a is equal to 1.5, if you see the yz value and consequently the Hn values, they are increasing continuously. That means they are growing out of bound. At n tending to infinity, we will be having Hn value which would be tending to infinity. Okay, that means this kind of system, they are unstable systems, and we have already discussed previously that when we place a pole outside the unit circle, it becomes unstable in nature. And how it is becoming unstable? This is the reason how it is getting unstable. Okay. Now coming to the IR filter design methods, there are several methods. Okay. One of the simplest method is the impulse invariant method. Then we have bilinear transform method. Then we have frequency transformation method. Then we have approximation of derivatives method. Okay. So coming to the impulse invariant method, so what it says is that we have a pole at s minus pi. So if you look into this Hs transfer function, so where is the pole? Pole would be at s minus pi equal to 0. Okay. So at s equal to pi, we will be having the pole in the analog domain. Okay. So what it says is that for every pole in the analog domain, we will be mapping a pole in the digital domain. And how will we do that? We will be using this equation 1 by s minus pi. It would be transformed to 1 by 1 minus e to the power pi t z inverse. Okay. So that means for each pole, we will be transforming this thing to this form. Okay. So as I told you that we will be having in the s plane a pole at pi, whereas in the z plane we will be having a pole at z equals to e to the power pi t. Right? What is t? T is the sampling period, which is nothing but it is equal to 1 by fs. Okay. However, this pole, it is in the s plane. Okay, so that is basically a point in the s plane, but we know that s is equal to sigma 1 plus j omega, and if we just replace it over here, we get these two equation. Okay, so modulus of z equals to e to the power sigma 1 t, and phase of z is equal to omega 1 t. Now if you look over here, if sigma 1 it is less than 0, that is it is in the left hand side of the plane, we will be finding it that the pole in the z plane, it would be within the unit circle. Similarly, when sigma 1 equals to 0, it would be on the j omega 1 axis in the s plane, and it will be on the unit circle on the z plane. And likewise, when sigma 1 it is greater than equal to greater than 0, then the pole in the z plane it would be outside the unit circle. Okay, so over here, so the main advantage of the impulse invariant method is that if we start with the transfer function of a stable analog filter, then the filter that we will be getting, it will also be stable. That means if you start with the transfer function of a stable low pass filter, and if you employ this impulse invariant method to convert it into a digital filter, then this digital filter will also be stable. Okay, now if we review our few of the lectures, then we can say that z equals to r into e to the power j omega, but it can also be regarded as z equals to e to the power st. Okay, now if you equate these two components, then we get something like this, and from here we get r is equal to e to the power sigma t and omega equals to omega t. So this omega, this is for the analog frequency and this is for the digital frequency. Okay, so our analog frequency, it is given by omega equals to omega by t, whereas from here if we see, our analog frequency is directly proportional to the digital frequency. But the problem over here is that this analog frequency, it can vary in the range of minus infinity to infinity, but in digital frequency we have only the frequency axis which is varying from 0 to 2 pi. So what happens after 2 pi? So the frequency components, they get overlapped onto the previously present frequency components, and hence one of the major disadvantage of the impulse invariant method is the many to one mapping. Okay, so due to this many to one mapping, we will be having this overlapping of the frequencies, which will ultimately lead to the aliasing. Okay, now when I talked about this equation 1 by s minus pi, it will be transformed to 1 by 1 minus e to the power pi t z inverse. This is for a distinct pole. I told you that if you are having a single pole, you can put the things over there. So these are for this equation is for the distinct poles. So under certain conditions, if you are able, even if you are given with a complex system, and if you are able to factorize that into the simplistic poles, and you get into position somewhere where you can get this kind of fraction, then you can use this impulse invariant method to directly implement the filter. However, if that is not the case, if you are having multiple poles and you are not able to solve that, then these equations for the multiple poles and the complex poles, it would come into picture. Okay, so usually in our lecture we will not deal with the multiple poles, because in most of the cases you will find, even if there are multiple poles, we are trying to break it down into the distinct poles. However, this kind of arrangement may appear quite frequently, so remembering these complex pole situations, it is important for you. So these equations need to be remembered by you. Okay, so coming to the numericals of the impulse invariant method, we have hs equals to 1 by s square plus 5s plus 6. So by partial fraction, if we break it down, we get this kind of equation. So 1 by s minus minus of 2 minus of 1 by s minus of 3. Okay, if you see over here, it is s minus of pi. You have to remember this thing. Over here it is given s of minus of pi. So that's why to bring it into conjunction with the previous equation, our distinct pole equation, we have to break it down in this way. Then we need to apply transformation, and after applying the transformation, if you see, we will be having this capital T over here. If T is given for you, then you have to use the T in the value of the T in your numerical. Otherwise, it is safe to assume it as T equals to 1 second. Okay. So, if you see, the transformation of this fraction, it comes out to be 1 by 1 minus e to the power minus 2t. Over here it was positive, so it becomes minus 2t z inverse, and similarly the second part also gets transformed over here, and then you can solve it, and after you have got the hz, you can realize the filter. The realization of the filter I will be going through it in the next class. Okay. So then coming to another question, the same thing, same way you calculate the hz. You are having this equation using the partial fraction. We break it down, then apply the transformation, and you get the stuff. Now there is another question where you may get t equals to say 0.2 seconds over here. It has been given. However, if you see hz is equal to, over here there is a multiplication of t, and the multiplication of t is to be done when we are having high sampling rates. So what do you mean by high sampling rates? High sampling rate, we will conveniently assume that it is for t less than 1 second. So for t less than 1 second you are having something, so apart from this transformation you have to multiply the hz with a factor of t. Okay, the rest of the method it remains the same. Now next, if you see, we are having another this numerical where we need to convert the analog filter with the system transfer function of this one. And if you see the numerical, it is just like in the normal one. We have to do the partial fractioning. Okay, and after we have done the partial fractioning, we can go for solving the stuff. However, if you go back, this equation is also available for you at your discretion, and you can solve the thing. And again, I would like to remind you, when you are getting these cos some values, you need to ensure that your calculator it is in the radians mode. Otherwise, if your calculator it is in the degree mode, then you may get incorrect results. Okay. Now coming to the bilinear transform method, it is one of the interesting methods which allows us in mapping the frequency in one-to-one basis. There is no many-to-one mapping over here, so we can avoid the many-to-one mapping of the frequency components if we use the bilinear transform method, but it is having its own disadvantages. Let's look into that. So you will find as we go forward that this bilinear transform method, it is mainly used for designing low pass filters. Why? We will be coming a few moments later. So in this method, it is said that S needs to be transformed with this equation 2 by t multiplied by 1 minus z inverse divided by 1 plus z inverse. Okay. Now, if we take this equation and try to find out the relationship between the analog and the digital poles, after lot of deliberations, if we take z on the left hand side and bring all the s on the right hand side, and again putting the value of s equals to sigma plus j omega, and doing all these things, we get to this equation, modulus of z equation. Okay. Now from this equation, if you see, if we put sigma less than 0, then our modulus of z, it would be less than 1. Sigma equals to 0, it would be resulting in modulus of z equals to 1, and sigma greater than 0, it would be resulting in the modulus of z greater than 1, which means it meets all the stability criteria of the for designing the digital filters. Okay. Now coming to the relationship between the analog and the digital frequencies. So again we will start with the same transform equation, and we will be replacing s to j omega and z with e to the power j omega. Why? Because when we are talking about the relationship between the analog and the digital frequency, that means we are only interested onto the frequency axis. Okay. क्या हुआ प्रत्युषा? Lost somewhere? Okay. So after replacing all this thing, if you see what we get this kind of stuff, and doing some mathematics, we get to this equation, omega equals to 2 by t tan omega by 2. Okay. In other words, digital frequency, it would be equals to 2 of tan inverse of omega t by 2. Now what happens over here, when analog frequency, it is varying from 0 to infinity, our digital frequency varies from 0 to pi. On the other hand, if the analog frequency varies from minus pi to 0, minus infinity to 0, omega, it varies from minus pi to 0. Okay. Now let us put this thing, and if we plot for the impulse invariant method, you will find that it is a straight line, right? However, in the case of bilinear transform method, if you see, it is increasing linearly up to certain point, and then it deviates and it is moving towards the pi, but it never reaches the pi. Okay. So as I was telling you, because of this phenomena, we are able to perform one-to-one mapping using the bilinear transform method. However, there is a disadvantage over here. If you see, near the lower frequency components, we are having a linear function. However, as we are going towards the higher frequency components, there is a non-linear mapping of the frequency components, and this is regarded as the frequency warping, and this is regarded as the frequency warping. And frequency warping, it is one of the problematic stuff which has been associated with the bilinear transform method. Okay. So another important thing is that over here we have drawn this analog frequency and the digital frequency relationship. Okay. Then what we have done is that we have sampled the analog frequency in equal parts. Okay. You may see that the width are different, but assume that these are similar. Okay. So that is basically a manual error. So while drawing, so we have drawn all this, sampled all these analog frequencies, and then we are, during this sampled the thing, we are looking into the digital frequencies also. Okay. Now if you see over here, in all the cases over here, if you look into the amplitude response of the analog filter, all the filters, they are having a flat response. Okay. On the other hand, and also if you look into the frequency component, the width of this frequency component, they are same. On the other hand, if you look into the digital filter, this amplitude response, where are you, Mahibalan? Where are you? Okay. So if you look into this digital filter amplitude response, again you will be getting a flat response, But if you now look into the sample frequency component, at the lower frequency components, the width are same. However, as we go towards the higher frequency, the frequency components, they are getting shorter and shorter. So what does this means? This means if you are having, say, a particular band of frequency, that particular band of frequency, it is being compressed in the digital domain. It is being compressed in the digital domain. Okay, so that means suppose you have 10 units of the frequency component to be mapped. So near the low frequency components, you will be having 10 units of the of whatever the allotment you say. However, when you are going towards the higher frequency components, that same 10 units of analog frequency components, they may be compressed into, say, 3 units, or say 2 units, or say 1 units. Okay, so it is getting compressed towards the higher frequency stuff. When discussing about the FIR filter, I had already discussed with you, if the frequency components, they are getting compressed within a particular zone, so what happens? It becomes very difficult for us to design filters over there, because the positioning of the poles and the zeros, it will be becoming very difficult. So due to that reason, uh, if you now can visualize, the bilinear transform method, it is mainly used to design low pass filters or band pass filters or band reject filters which are working in the low frequency domains. Okay, anywhere where you will be having you have to design something where you have to pass the high frequency bands. Under those circumstances, this bilinear transformation method will not help you. Okay, so now all of you know that why we are having this maximally flat response while we design the this filters using the bilinear transform method. Okay, and second stuff we have already discussed. Now coming to the numerical, suppose we are given with this transfer function. Okay, and we are asked to convert this analog filter into a digital filter, then by the bilinear transform method, then we will be using this transformation equation, and you will be putting this equation for S. Okay, now once you do this, again there is nothing for t equals to 1 second, so we will be taking t equals to 1 and we will be getting the HZ, okay, the transform function. Now in some cases you may be provided with Sn. Okay, so what is Sn? Sn is normalized frequency components. So this Sn, it is equal to basically S by omega c. Okay, so if you get something like this, then what happens? So suppose you are having this cutoff frequency of 0.4 pi. So what you have to do, you have to find out this omega c. Okay, and this would be the analog frequency. Okay, because S is for the analog frequency components. Okay, so we have to calculate the analog frequency. Over here what we are given with, we are given with the digital frequency 0.4 pi. Okay, so that's why we had to convert this frequency, digital frequency, into omega c to get the analog frequency, and then after we have got this, we have to replace Sn with S by omega c. Okay, so if you see over here, we have replaced with Sn with S by omega c, and after doing this, the rest of the method, it remains the same. Okay, next coming to the designing of the Butterworth filters, there are other types of filters also, including Chebyshev filters. Okay, but we will not be going into those due to the shortage of time. So we will be mainly concentrating on the Butterworth filter itself. Okay. So herein, when we talk about the Butterworth filters, the order of over here it is given that the order of the filter is given as 2, and cutoff frequency FC it is 1 kilohertz, and sampling frequency is 10 to the power 4 samples per second. Okay. So it has been given that we have to use bilinear transform method over here. Now FC equals to which is basically the digital frequency, it is given by capital FC divided by Fs. Okay. Now the omega c, it would be equals to 2 pi Fc, and we get the digital frequency as 0.2 pi radians per sample. Now omega c over here, again by using the bilinear transformation method, we will find out the omega c, the analog frequency, because we are designing the, or we will be emulating the Butterworth filters, which are the analog filters. Okay. Now from here, the order of the filter, it has been given as 2. So we know that there will be 2 poles, and for determining the location of the poles, we are given with pi equals to plus minus omega c e to the power j capital N plus 2i plus 1 pi divided by 2n for I varying from 0 to n minus 1. So n is equals to 2, so n minus 1, in this case it is 1, 0 and 1. So we will be having I equals to 0 comma 1. Okay. Now we will put this n value, n is 2, this is 2, omega c we have just calculated. Now we just need to change the values of I. So I first will be putting as 0 and 1. So accordingly we get P0 and P1. Okay. Now if you see, we will be getting 2 points plus minus because of this plus minus sign. Okay. So we will be getting P01 and P02, P11, P12. Now we will be putting these points in the S-plane, and once we have put these points in the S-plane, we know that we cannot put any poles on the right hand side of the S-plane. So we will be rejecting these 2 poles, and we will be moving forward with the other 2 poles. Okay, we will be moving forward with the other 2 poles. Now what is the equation? The equation is, for getting the transfer function, it is Hs equals to omega c to the power n divided by s minus s1 multiplied by s minus s1 conjugate. If you see, P01 and P11, they are basically conjugate of each other. Now the same thing, omega c you have already calculated over here. These locations you are already having. Okay, then you have got Hs. Use this transformation and you will be getting the equation. Okay, then you can go for the realization of the IF filter. We will be discussing a bit later. Okay. Now there can be another type of question just like this. So we have using bilinear transform method designed Butterworth filter which satisfies the following conditions. So the pass bands have been given. So this is the pass band, this is the stop band. So gain in the pass band, it is 0.8, gain in the stop band, it is 0.2. okay, omega p pass band, it is 0.2 pi, and omega s stop band, it is 0.6. okay, I hope everyone knows how we have got these values, right? It is from the designing of this filter response. Okay, so now coming to the determination of the specification of the analog filter. Now we are given, we know that analog frequency, it is equal to 2 by t tan of omega by 2. So omega p, it is given by 0.65, and omega s, it is 2.75. So we are having this equation, AP equals to 0.8, AS equals to 0.2, omega P equals to 0.65 and omega S equal to 2.75. Okay. Determine the order of the filter N. Over here, if you see, the order has not been given. Okay. So in the previous case, we were having the order which were given. However, over here, we have not been given with any order. So the order of the filter, it would be given by 1 by 2 multiplied by log of 1 by AS square 1 by AS square minus 1 divided by 1 by AP square minus 1, then divided by log of omega S by omega P. So if you solve this, you will be getting something, but our order of a filter cannot be in fraction. So we have to take ceiling value and not rounding off. Okay, we have to take the ceiling value. So that makes the order of the filter capital N is equal to 2. Okay. Then we have to find omega C, which is the cutoff frequency, because we also need the cutoff frequency. So omega C, it is given by omega P divided by 1 by AP square minus 1 to the power 1 by 2n. Okay, and we get 0.75, and the rest of the numerical, it remains the same because we have got all the things what we will be needing. Okay, we have the omega C. Now we already have the n from here. Okay, so we just have to vary the I values and we'll be getting the thing. Okay. So the next topic I will start on Monday.